Hello everyone, welcome back. Today in our Stack and Queue series, we are going to learn a very important topic, and that is called LRU Cache. It is a very widely used algorithm, and from your exams or your interview perspective, do expect a question on this. So let's start. First of all, we need to understand what is a cache and why we need a cache. What is a cache? Why we need? We are talking about it. What is the reason behind it? So if you understand how a typical program works, so your code is running out here. Suppose this is your module, this is your process, right? And you are writing some code, okay, employee details and all those things. And if you want to check how many leaves are remaining for an employee, so basically you are going to query a database. Right? So we can assume that there would be another process running for the database, and you will give a query and it will give you the data back. Now, this database also eventually go to some file that is stored on the hard disk and get the data from there, and then you will get the data. So if you see carefully that there is an IO involved here, input output, with the disk, which is not very efficient because it might be possible other process might be using the disk. Okay, so what cache is, I'm just telling from very high perspective. There are very different types of caches. This is just from a single program perspective running on a machine. So what cache is, you will temporarily store in some short memory within this process only, not outside it. In some very short memory, you will store the data that you use more frequently or more recently. So we can say what a cache is. A cache is something that stores the least recently or frequently used data. Why? For faster access, as we don't need to perform the IO to disk. This is a cache. This is the role of a cache. This is the need for a cache. And this is applicable for every process, every process, because there is some data that you most recently that you need more and more frequently. For example, you need the authentication key of the user who has logged in. So you won't go and fetch it again and again. You just store it somewhere. Very typical usage of example of a cache. So that is a cache. That is the role of a cache. Now I have used two words: least recently or frequently used. And these are the two algorithms, LRU and FRU. Least recently used and least frequently used. Today we are going to learn about LRU, least recently used. Before going forward, some of you might ask why we cannot store everything in cache. So there are two reasons. Why not everything in cache? First of all, it is not persistent. With persistent means if your programs goes out, your cache will be lost. You can say that, okay, I will write it to the disk, but then IO will come. So that is going to take time. There is a concept of having a persistent cache. I'm not denying it. But again, it is some kind of an advanced one that we can cover later in some other video. Here we are just understanding the concept. It is not persistent. It is costly, right? Because this data will be stored in RAM. Your hard disk can be in terabytes, but your RAM of your machine is in some gigabytes. It is very costly. So that is why you need a main, and you can see these are the limitations for the cache. Hence, we need main storage, which you can say hard disk or any persistent storage, to store entire data. That's why we cannot store everything in cache. We only store what we need, as it said, least recently used. So if I take example of a system that say marks the attendance for employees, so whatever employee information is least recently fetched, it will store in the cache. And when the cache becomes full, what was stored last will be evicted out. So there is something called eviction policy. Right? Eviction policy for a cache determines when the cache becomes full, what element will be evicted out to make space for the incoming one. Okay. And if you take example of a queue, what is the only property of a queue? First in, first out. So whoever was the first element pushed into the stack, it will be taken out. And if you just change the words, what element was last inserted, we will keep those, right? The elements which were inserted last, elements inserted last were used least recently. So we are keeping those, and the one which was inserted first will be popped out. That's why queue data structure is used in implementation of caching algorithms, especially LRU cache. Okay, so we covered what is a cache. This part says why we need cache. Then we say what were the limitations of cache, right? And then we understood about the eviction policy that is there and why a FIFO based queue is used for LRU cache, least recently used cache. Before going forward, a couple of more things, and that is, when you are designing a cache, what is your primary motive? One, we understood, okay, the data that we have accessed more recently, we want to keep it. That is what we understood. That's great. Another one is the access to data. In the cache must be as fast as possible. That means when we come to time complexity, it should have minimum. And you all know the minimum time complexity is constant time. So when we are designing our LRU cache, we have to make sure we have to meet two requirements. Two must requirements of LRU cache. First one is it must store least recently used data, and second one, all operations must be in constant time. So these two requirements we need to take care for when we are designing the LRU cache. Now let's move to the design. So I think the requirements were moved up. So I will quickly write the requirements here so that we don't lose them. Our requirement, there were only two requirements. I will write at top. One is we have to follow the LRU principle, and second one, all operations should be constant time. These are the only two requirements that we have for our design. So let's start with our design of the LRU cache. So first of all, we should be having a queue. We are having the queue only for 5 elements for easy understanding purpose. This is our front where things will be popped out, and this is our back where we will push the things in. Okay, great. So only a queue can do the job for the LRU cache. You keep on pushing from the back, you will keep the popping out from the front. But if you want to search something whether it is present in cache or not, when you want to access it again from the cache, it will not be constant time. It would be the linear operation equal to size of the queue. So which means our second requirement won't be fulfilled if we just use a queue for LRU cache algorithm. Now I encourage you to pause this video here and think what we can do to make even searching constant time. Okay. Those of you who have guessed, great, thanks, congratulations. If you're not, don't worry. Let's understand how we can do that. Okay. So what we can do is we can also maintain a hash map for storing the elements. Great. So what we are going to store in hash map is the key will be the same, the value that we are storing, and its value, the value for the every key will point to the element in the queue. So let's say we have pushed few elements in the queue, 5, 4, 3, 2, 1 in this order, then this will be stored somewhere like this, because you don't know in which order the elements will be stored in hash map, and these will be pointing to these like this. Okay, so we will quickly see with an example how this works, and before that I will write the algorithm. Okay, so I'll just undo this so that we can take the example quickly. First of all, I will write the algorithm. Let's see the algorithm first for the LRU cache. So there can be two operations that we want to perform. First of all, get element and insert element, and one more can be remove element. These three operations we want to support for our purpose. Now algorithm says as a first step, if cache is full, then remove the element at front, and then push new element at back. Else, that means the cache is not full, push new element at back. And second one is to get the element. When you say I want to get an element, you can say check if element is present in hash map. Now let's see our algorithm with an example. Let's see we want to insert, and I'm going to take this in random order, 3, 5, 1, 4, 2. This will make our cache full, and then I'm going to have another element 6, and we will see how that will perform. Okay, let me change the color. Now first we will start from this point 3. So first of all 3 came. Okay, we will check if the cache is full. Not. We will go to the else part here. We will push new element into the queue and also make an entry into the hash map. So we will push the element into the queue. From the back we will push. So it will, I'm writing out here so that we can write more elements. Okay. And we will make an entry in hash map. Let's say it comes at this point. And the location of that element in the queue, its address, we will store in the hash map so that it can point out here. This will make our operation O1 when we want to search something in the queue. If you want to search something, point number 2 in the algorithm, you can check whether it is in the hash map. How much time it is going to take? O1 time. This one is going to take O1 time. I'm writing the time complexities here. This is going to take O1 time. Push element add back is going to take O1 time. So you can see that every operation is an O1 time operation, constant time operation here. So when we push 5, okay, 5 will be pushed here. Suppose it came here. We can say it is pointing out here. Then 1, 4, and 2. 1, 4, 2. In any order I'm writing, doesn't matter. So we have a mapping between the queue and our hash map. We have to maintain this mapping for every case. Great. Now let's see 6 came. What our algorithm says, we have to remove the least recently used. Which was least recently? Which was pushed first? 3. So what we will do, remove the element from at the front. So we will remove 3 out. 3 we will take out. So these all we have already pushed. 3 we will take out. So when we take out 3, we will make sure that its entry is also removed from the map, because we have to maintain the mapping, right? And for our easy perspective, I can remove this part and make the space here so that I don't want to shift the elements. Now we have space in our queue. So if you see point number 1 in the algorithm, if the cache is full, we remove the element at front. That's what we done in O1 time. And now push new element at the back. It's simple. We push element in the back, insert it into the hash map, and will do the mapping. If you are not able to follow, I please request to go back, rewind, and listen again. And keep on thinking in your mind how each and every step, each and every operation is done in O1 time. Now, one more thing is left. If you access an element that is already present, let's say you want to access 5, then 5 should come at the back, because it should not be evicted when 7 is inserted. Are you following me? I'm repeating it again. Now, if you see the queue, the element that is next going to be evicted if you try to insert 7 will be 5. But assume your program uses 5 and it is read from the cache only. Now it is was not used first time or the last one to be used. It is the least recently used. It should not be evicted. So whenever you get an element in the cache, you have to do a remapping. And how that is done? That is again done in overtime. What you will do is you will remove the element from the queue. You will remove its mapping, but you will not remove it from HashMap. What you will do is you will remove it from the front. You will push it at the back and you will remap it in the HashMap. And now when you are going to insert 7, the element that is going to be evicted out is 1, which we already saw when we evicted out 3 when we had to insert 6. So you have to make sure, this is a very, very important point. If you able to find an element in the cache, so you have to remove it from the cache and insert it at the back so that it comes at the least recently used area. It is not evicted out. And even if that element is present in between the queue, then also you have to do the eviction and insert it at the back. And make sure you keep the mapping with the HashMap. Great. I think that's all for the LRU cache design. I hope you followed it and liked it. If you have any concerns, questions, please let me know in the comments below. And if you want to have more videos, say for FRU or least frequently used, LFU, sorry, then do let me in the comments below, and I will do create a video on that one. So with this, thank you. See you again. Bye bye.